Hi everyone! Do you remember the lightning shader that I was creating in one of the previous videos? This time we'll try something similar but less chaotic, so the code will be significantly shorter. I'll show you how to transform a simple line into something like this. I probably didn't mention it at the beginning, but I work in Godot 4. It's 4.2.1 stable, the latest version at this time. So the shader will create is primarily intended for a material in this game engine. However, the shader code doesn't contain anything specific to Godot, so it should be easily transferable to other systems. So we'll start as usual by creating a 2D scene, which we'll name, for example, lines tscn. Let me do that. Right click, create new scene, 2D scene. This is correct. Lines and OK. Now we need a child node that would be of color type, and let's set the usual dimensions, which are in our video 600 by 400. And of course we need a material, new shader material, click it and create a new shader of the canvas item type, and we'll put it to the right folder, shaders, and create, and click to open in the editor. So we'll prepare the skeleton of our algorithm. Since we'll only need the fragment function, we can delete the rest, so we don't need vertex. Okay, and white. Great. And we'll start with the usual translation of the coordinate origin to the center and setting the correct aspect ratio. So we need a uniform parameter to define the dimensions of our rectangle. It's a vector 2 resolution and starts at some default value, which is equivalent to our current dimensions. Okay, and the fragment, so vec2 uv is uv and subtract 0.5, because as you know probably from previous videos, in UV coordinates 0, 0 is at the top left corner and 1, 1 is at the bottom right. So if we want the origin 0, 0 to move to the center, we need to do this kind of transformation. And of course we are not working on a square but on a rectangle, so let's fix the aspect ratio. UVX would be multiplied by the resolution X divided by resolution Y. Okay, so much for the transformations, and now we need to define the color of the particular fragment pixel, so it would be vec3 color. We'll start at black color, which is 0 of course in all components, and let's assign it to the variable color. And of course color is vector 4, so we need to use color and alpha value, which would be set to 1. Alright, so everything is black. This is correct. As I mentioned, we'll start with a simple straight line. Unlike the lightning effect we created from top to bottom, our effect will be displayed horizontally. So we'll add the drawLine function and implement the code for the line. Our effect should have some color, so first we'll add a uniform parameter for selecting the color, and then we'll use it in the code. Uniform parameter, okay, we'll put it here. Uniform vector 3. Let's call it line color, and it's of the type source color, so we'll get this nice color picker in the inspector, and I prepared this nice green default color. Okay, if we take a look at the what's wrong, vector 3, of course, sorry, and here we go, shadow parameters, it's green right here. All right, and now dimension function. So vec3, draw a line. It takes parameters UV of the current pixel coordinates and of course the color. So to create a simple line, we just return an absolute value of the y coordinate, because we are creating a horizontal line, and multiplied by the color value. So this is the function, and now we need to use it in the code, so we'll simply add it to the color variable. Color is increased by the result of this drawLine function with parameters UV and line color. Okay, so we have something, but it's displaying in inverted colors and the line is too thick. First, let's narrow it down, which is best done using the smooth step function. So in this we will return a smooth step, a result of the smooth step function with the boundaries from 0 to, let's say, 0.1. Let's start with that and we'll see how it goes. And bracket. Okay, that's better, but still too thick. Let's try 0.01. Now it looks like a straight line. And of course, to invert the color, we'll subtract the result of the smooth step function from 1. So we need to do this and another and bracket. That's it. Now we have a nice green straight line. Since the upper limit of the smooth step function determines the thickness of the line, it will be advantageous to create another uniform parameter for it. Let's put it here. Uniform float line thickness, and let's give it a hint range so we can easily select it from the inspector. It would start at 0.01 and 1, of course, and the step would be this one, and let's do it with the initial value, for example, 0.05. Okay. By the way, we'll probably be using the smooth step function and its inverse variant, 1 minus smooth step, in multiple places in the code. So we can simplify this using preprocessor directives. Let me show you. So we put it there and hash define as smooth step. So this simply says the preprocessor that each time it encounters s as a function, it would replace it with the smooth step function. So this is the first one, and to create the inverse one, it will be a little more difficult because this time we need to work with the 1 in the formula, so it's not simply a function name replacement. We'll also use the parameters x, y, z, because as you can see, smooth step function has 3 parameters: low range, high range, and the actual value. So this is x, y, z, and it would be replaced by 1 minus smooth step x, y, z. Great. So we can already try it here, and this would be this would be is, and I think we can get rid of this bracket now. Great. Nothing changed, which is great. Okay, now let's enhance our line. It would certainly look interesting if its thickness varied based on the horizontal position of the respective pixel. Let's try multiplying line thickness by the absolute value of UVX. So first we will use line thickness. I forgot to do that. There it goes. And as I said, we'll multiply that by absolute value of uv.x. Let's wait. Okay, not bad, but could be better. Let's apply the smooth step again. So instead of just absolute value, we will use S as a short for smooth step and start at, let's say, 0 and at 0.9 in the end bracket. Okay. It looks better, but there is still a gap in here, so let's get rid of it. Let's fix it by lowering the lower limit. Let's try minus 0.1. Almost there. 0.2. Now it's connected. Great. So the foundation of our effect is ready. Now we just need to add a bit of a ripple to our line, introduce more lines with different parameters and animate the result. Let's start with the rippling, for which a naturally wavy trigonometric sine function works well. Let's do it by shifting the y-coordinate of the current fragment. So we will do it right here. uv.y would be increased by absolute value of uv.x to make it a bit symmetrical and multiplied by sine of uv.x and semicolon, of course. Okay, something happened, but it's not exactly what we expected, right? Let's fix it with another inverse smooth step. Basically, many similar effects are based on smooth steps, absolute values, and trigonometric functions, and just combinations of these three. So we will apply inverse smooth step here from 0 to 1 this time, and the bracket here. Okay, looks much better. Let's start to introduce more parameters that we will need for shaping the lines. I will put that here at the uniform variable section, uniform float speed. Yeah, as you probably already know, we will animate the effect, so we need the speed parameter to control the animation speed. And now uniform float amp coef. So we will be working with these periodic functions, and these functions are based on amplitude and frequency. So we will manipulate these values to create various curves and to combine them into the final effect. This is for the amplitude, and I will create a similar variable for the frequency, frec coef 0.5, for example. Okay, to animate the line, we will multiply the speed by the internal time variable. Let's do it here. So let's define a variable called shift, because we will be shifting the position of the particular pixel, and it's, as I said, time by speed. All right, so we will fix the drawLine function now, the function signature, the parameters, to incorporate new parameters. So we will add float shift and float frequency frag. We need to do the corresponding changes in the fragment function where we call drawLine. So it would be shift, and let's start just with 1 for the frequency. We'll change it later. Okay, and of course we need to use it to animate the line shape. So let's get back to drawLine and here we will add it to the sine function argument. So it would be plus shift by frequency. Okay, not bad, but there is still only one line. Let's add another uniform parameter called iterations to determine the number of lines. Uniform float iterations. Again, let's use the hint range. That would be from 1. We don't want 0 lines, of course. Maximum, let's say 20, and the step is 1 this time. Okay, and this is the initial value. We will start with 5 lines, and now we need to use it at the fragment function to draw all lines with variable parameters. So this line, which is responsible for creating the curve, we will put into a cycle for float I from 0 to a number of iterations and increased by 1. Okay, open, close, indent, and of course now we are creating 5 identical lines, so the colors are adding up and creating this white effect in the middle. We want to add some kind of more shift based on the I index. So for example here, plus I multiplied by 0.4, and now that's better. And here we will finally use the frequency coefficient. Okay, by the way, the values 0.4 and 1, they are just randomly selected. Perhaps they could be converted into uniform parameters as well to enable even more tweaking. And because the amplitude of our wave is too high, we will use the amp_coef parameter, this one, and another sine function to achieve the final effect. Let's do it. So this is correct, this will stay as it is, and we will add just multiplication by the amp coefficient, and okay, that's better, but still we can add a more pseudo-random factor by multiplying by sine uv.x plus shift, sorry, shift of course. There we go. Well done. We can play with the shader parameters to see what we can do with this cable. So let's, for example, I don't know, increase the iterations. Where is it? Here, from 5 to 20. Change the amplitude, frequency, line thickness, or even thinner. We can change the color to something more fiery. This is very nice, I guess. You can do many things with that. Let me just revert to the original set of parameters. Okay, so it seems that with a high number of iterations, increased to 20, there is an excessive brightening of the cable edges. We can solve this by multiplying the final color by another coefficient. Let's add it as a uniform parameter called brightness. So uniform float brightness with a hint range from 0.1 to, let's say, 20, why not, and increment 0.1, sure, and let's start with 0.5, and we will use it at the fragment function right here. Color will be multiplied by brightness. Let's wait. It looks better. Now it's possible to increase or decrease the brightness. Let's try it out. Okay, or change it into basically only white looks good in both ways. All right. This can be also utilized as a dynamic effect by changing this parameter from GD script. For example, if the cable is hit by some shot or beam, you can work with that and create all kinds of this effect. And that's it. I hope you liked the effect and the algorithm, and you will find a use for it in your own project. You might even discover other ways to enhance it further. So have a nice day and see you in the next video.